So, we have our an original function. And if you go back to algebra, when you talk about original functions, you talk about functions, you talk about like increasing, you talk about decreasing, and what else?
Zeroing out.
Okay, is it a constant? How about, what do you really care about in physics with quadratics? Max and mins, right? Extremas. So, if a function is increasing, it cannot be decreasing. A function can go, this is, you're filling in your boxes.
Yeah, the first two boxes.
Yes,
Right there,
yes. No, box by box. A function can go from increasing to decreasing, and that would give it an extrema. It could go from decreasing to increasing, and that would give it another extrema. These are called max, those are called mins. So ext is extrema. It is either a max or a min when you use that word. Okay, functions can also be smiley faces or crowns. And what did we talk about when we talked about being a smiley face or a crown? Starts with a C. Somebody said it. Concavity. So concave up, concave down. Concave down is a frown. Concave up is a smile. Is it positive and happy?
Oh, really?
Okay, if something changes from concave up to concave down, what's that point called? There's a point between them. What's that point called? I think that's like the short term for it. It's called POI. A point of inflection.
Oh.
Makes sense.
So, if this was your function, we'll call this f. F has a extrema at A. You don't have to draw this. I just want to do it while I walk you through this. And an extrema at B. Right?
Yeah. Mm-hmm.
Okay. Where is this function increasing? We'll call this, we'll start at 0. We'll put a point in here, call it C. Make this point D. Okay. So where are we increasing?
0, 0, B, or B to F.
No, F is the name of the function. And technically that would be a bracket because our function ends. But they're not very picky about that. Okay, where's it decreasing?
A, B.
Where are my extrema?
A.
Where is it concave up?
C to D.
C to D. And concave down. So can you guess what the point of inflection is? Okay. Those are the key ideas for F. That's what you've been doing. You know how to describe this. You know how to do this. The problem is, in physics, F would be like your position function. Right? So you're not, sometimes you're given the position, sometimes you're given velocity. And it asks you about position. It might ask you, is the particle moving forward? A particle moving forward would be increasing. So in calc and in physics, we oftentimes talk about the derivative, which is f prime. F prime and f have a relationship. If the original function is increasing, what did we say the derivative was in terms of what we've been talking about. The derivative has been what? What was perfect? The derivative is the limit of the slope of the secant. Keyword slope. The slope of the secant would be picking 2 points on F and finding a slope. If I picked point 0, I don't want to draw on it because it'll ruin my marker, and point A, is the slope from 0 to A going to be positive or negative? Positive. Guess what? If you find the derivative of F and you plug in a point from 0 to A, your derivative will be positive. If I plug in a point from 0 to B on my derivative, what is the slope of that secant going to be? Yeah, I'm trying to avoid the block. Sorry. So if the original is decreasing, the derivative is negative. What do you think happens at an extrema? Yeah, it's going to be a horizontal slope, which would be 0. Does it make sense if something goes from increasing to decreasing, where it changes as a 0, something would go from positive to negative, you have to cross the zeros? Okay? Here's what's super nice about derivatives. If it's concave up, we'll look at this. What do you think would happen if it's concave up? What's happening? So this is concave up, right? From C to D. The slope of the secant from C to D is almost doing, see, this one's tricky because I kind of drew it at the point, so it wouldn't quite be there. This is where I said it's tricky. It's actually going to be increasing. So that's what I said. It's hard to see because of the way, like, I drew, like, this point wouldn't necessarily be right there at B. Like, it could be, like, up here. Concave up, concave down, and POIs are actually the first 3 of F. So if something is concave up, on its derivative, it will be increasing. If it's concave down on its derivative, it will be decreasing. So what do you think happens at a POI on its derivative? It'll be an extrema. What's bothering me? It's not separate. It does, right? Like, this column is your second derivative. So in physics, the second derivative would be the function that follows velocity, which is acceleration. Think about velocity. If velocity is a constant, what's your acceleration? 0. Velocity is a constant. What's your acceleration? So think of that as a graph again, right? What would the slope of that tangent line be? Because it's a horizontal line. Like, do you see how that works? If you picked any 2 points on this line and you found the slope, that's your denominator. I'll call this C. You get C minus C. So a constant velocity is a 0 acceleration because of cap. Just FYI. That means if these are numbers, they have no relationship to f prime. This part does not exist. There is no relationship to f increasing on the second derivative. There is, however, a relationship if f prime is increasing, decreasing, or an extrema. What do you think we know about the derivative? increasing on the derivative or it's concave up on the original, the second derivative will be positive. So these three lines, here's what's nice about the chart, right? These three lines transpose to here. These three lines transpose to here. So if you just memorize the first 9, it repeats itself. I promise you, this chart will get you further than anything else. So questions may arise. So again, you can kind of see here, it looks very similar to the graph I drew. We're just going to talk about it. Graph the derivative of the function f, whose graph is shown below. Discuss the behavior of f in terms of the signs and values of f prime. So we're given f, we want to graph f prime. What do we know about f prime immediately? What's the easiest thing, thinking back to that chart, that we can plot on this derivative graph? I look for 2 things right away. Okay, I like POIs and what other points? Extrema. Extremas are 0 on the derivatives, right? So if C is a max, its derivative is a 0. If F is a min, its derivative is 0. That's what I look for first, because they're the easiest points to graph. They're telling me my slopes. Why does that kind of matter? Well, what did we talk about? The slope of the original is the value of its derivative. So if the slope at A to B, this slope is 4, that means A is kind of like at 4. And then it's kind of telling you like where things are happening. Think about this. The slope is 0. My point was at 0. So from A to C, what should the derivative be doing? It should be what? No, the original is increasing. Think about this. The original is increasing. So the derivative is, the original is concave down. Would you not agree? So your derivative needs to be decreasing. So it is positive and decreasing. So it's going, yeah. It's going.
So it's a concave up.
So it's positive and decreasing. So again, at A we have slope 4, at B we have slope 1. So there's your positively decreasing function. D would be considered my what? On the derivative. What's happening here? It's going from a frown to a, so D is our, yep. So the original is doing what from C to F? We are decreasing. My slopes are negative. If the original is decreasing, the derivative is negative. So that means here's my 0. These points are all down here now. So this is 3, negative 1. Yep. You have an extrema at this POI. So that means a POI has to be your lowest point. What? It should be like there. Here's E. F has to be 0. Actually, this point here could be a little lower, probably. There's a 0, and then it connects.
Wait, what point?
I missed.
3 what?
Like, So D we know is at -1. So like this point here needs to be just like a little bit lower because it's your extrema. So I just kind of made it like maybe like -1.5. We don't know it as precisely as the other points.
So D
I
and E-
cannot make that. What?
So should D and E be equal and like an extrema of 4?
Yeah. Like you could make this point. I know, I kind of had them equal and then I felt like this was not lined up with 1. Can't see. So here's your D, right? So like, that's probably better. That's probably why I can't connect them either. I'm off on my board. My pen is off so much. I give up. Yeah, like your POI is maybe a little further this way.
Okay, so D's 1. Or like
It's
5.
not quite your
It's
POI.
not quite all the way there.
Because if you pull back a little bit, which they should have given you a point for your POI, but we'll say our POI is more than here.
Okay. Because I was very confused for a second.
I know, because like I'm looking at it, like, and I think sometimes like when I look at my board, it's not like the same as.
Like when you look at it from such a small.
I know. I have trouble on the board looking at things. I have it printed. I should have just looked at my real notes. Hmm?
We're supposed to graph it on the,
I gave you the graph line on the next. Yeah.
My graph
I did it on the.
That's okay.
My graph looks like this.
It was easier for me to do it on this because my other one's on my next slide. Yeah, see, look, there you can see I have my -1s perfect. I did my 4 a little lower. It's okay. You can keep it on the graph you had it on.
1, 1, 2, 0.
Mm-hmm. Oh, I kind of told you, like, can't you see how this is a quadratic? And you definitely could tell the previous or the given one would be an odd function. Oh, he gets it, right? There you go. Cubics become quadratics, quadratics become linear, linear become constant. Again, doesn't it almost make sense? A constant becomes 0. Like, a constant velocity, 0 acceleration, linear distance, constant velocity, 0 acceleration. Yeah. The power rule all comes together. I said, I like chapter 3 because I feel like it kind of. Because you don't understand a derivative and a limit in 10th grade.
It would make graphing in physics a lot more sensible.
Not
That's true.
disagreeing.
We did graph in physics and it was kind of difficult.
I tried to help my kids, so like my algebra 2s would be in physics, and they would have no idea what quadratics were yet because we don't get to them till chapter 5. I totally switched the order of the book. I skipped chapter 3, taught chapter 5, and then went back to chapter 3, which is systems of equations, because they were like, we don't know how to graph quadratics. He thinks we know how to graph them. We don't know how to find max and mins of quadratics. And I was like, breathe. We'll just skip some chapters, go do this, and come back to it. I was like, no big deal. Math can go in different orders. All right. The biggest thing I saw we messed up was like left and right hand continuous on our limits quiz. Well, there's left and right hand derivatives too. But think about it. A left and right hand limit is a derivative. A limit is a derivative, essentially. That's what's happening. You just have to take the limit of a slope. So here, your limit as h approached 0 from the positive would be what limit? What limit would that be? If it's from the positive, it would be a
Right.
there we go.
Alright.
It's okay. I was waving. So the limit as h approaches 0. And then, again, all we know now is the slope of the secant. So that's like your f of a plus h minus f of a. all over h. What would the left-hand limit then be? Yep, but from, yep, so this is the left hand, oh, in that drawing, this is the left-hand one. And so on. And it would be the same formula. So these are your left and right hand limits. We can now actually refer to these as left and right hand derivatives. So these are also derivatives. Functions that are not continuous would have left and right hand derivatives. So when you have a piecewise and it has a jump or a break, then you would look at a left-hand derivative and a right-hand derivative surrounding that point. So that's kind of what's happening in this example here. We have the function x squared for x less than or equal to 0. So that would go through 0, 0, negative 1, 1, and negative 2, 4. And then you have the other function, 2x, that would go through 0. And then it would go up 2 and over 1. So if it says, show that the following function has a left-hand and right-hand derivative at x equals 0, but not a derivative at 0, what that means is that we can find the left and right-hand derivatives, but just like before, if the left-hand limit doesn't equal the right-hand limit, then the limit does not exist. If the derivative from the left doesn't equal the derivative from the right, then the derivative does not exist. So this will look like the limit as h approaches 0. Am I coming with the red function from the left or the right? So it'd be the negative. F of a plus h, in this case, would be a plus h squared minus a squared all over h. What's my a? 0. So it'd be the limit as h approaches 0. And then if you wanted to plug in your a's, you could. So you would be 0 plus h squared minus 0 squared all over h. See why I plugged in my a values? So we get h squared all over h. So it would be 0. How about the limit as h approaches 0 from the right? So now we're talking about this function here. So that's like 2a plus h minus 2a all over h. So 2a plus 2h minus 2a. Once again, my a would be 0, so it would cancel out either way if I plugged it in or didn't. What's the derivative then? So think about even what you know. The derivative of 2x would be 2. Therefore, the slope of that function is always 2. So like this limit here, the limit from the right, its derivative would look like this. The derivative of the other function, well, what do we know about the derivative of x squared? It is 2x. Yeah. So it would have looked like that. So the orange is the derivative of the blue, the purple is the derivative of the red. Do these derivatives match up? No. Therefore, since the derivatives don't match up, the derivative at x equals 0 does not exist. That's going to lead us into, remember I told you we're going to talk about the words differentiability? This function is not differentiable. So you have to be cautious of piecewise functions being differentiable. That pretty much summarizes 3.1. So far we've talked about average rate of change with respect to an interval. This has a fancy name called the difference quotient. So sometimes your textbook will refer to the difference quotient. The difference quotient is the same thing as what? There we go. The difference quotient is the slope of the secant. Instantaneous rate of change is the slope of the tangent derivative. So average rate of change is slope of the secant. Instantaneous is slope of the tangent. And then in general, we can say that the derivative is the instantaneous rate of change. So the idea is that you now know the derivative is the slope of the tangent, which is the limit of the secant. You can look at these problems in terms of like economics. So companies could look at them in terms of manufacturing. So this is like, hey, what does this mean? So it says a manufacturer produces bolts of fabric with a fixed width. The cost of producing X yards of this fabric is blank dollars. What is the meaning of the derivative and what are its units? So we'll call our function C equals f of x. The cost equals f of x. What would the derivative be for cost? If cost is the production of X yards per fabric of dollars, what would your derivative be? What's a derivative in general? It is a blank of blank. Okay. It is also a rate of change. So if the top part of the cost function is the production of X yards, its derivative would be the change in yards over the change in dollars. This is called marginal cost. Good, flip these. I did it. Because I wrote X yards of fabric. And think about it, if you talk about cost per dollar, like dollars per yard, as I wrote it, I was like, I totally flipped the words yards and dollar. Oh, flipped as yards and dollar. So that your cost is dollars per yard. Sorry. Let's do it again. For whatever reason. Alright, so let's look at an example. So the example is, what would it cost to produce 1,000 yards? So what would your marginal cost be? Do you have an actual function on your paper, don't you? No? Or just what I've been writing? Yeah, exactly. So f prime of 1,000 equals 9 tells you what? The cost to produce 1,000 yards costs $9. That's probably pretty comparable. As the costs increase or the yards increase, what do we expect to happen to the production cost? Careful. If a company mass produces 5,000 yards, is it going to cost them more to produce 1,000 yards or 5,000 yards? Think about product efficiency. No. 5,000. Because
Per yard, you mean? Like how much will it cost per yard?
right, so this is the cost to produce 1,000 yards is $9.
5,000 would be more. Would be less per yard. Yeah.
Because you're already paying all the bills and all the workers and everything to be there. So like, that's why things are mass produced in companies. Because typically if something costs less per yard, so it says which is greater, what about, I don't know why none of my words typed in. So the cost of producing X equals 500 yards would be less per yard than only producing 50 yards, taking into account fixed costs of production. So that's what I said, like the cost to do 5,000 would probably be less than 1,000, but then you have to talk about like, where would it be its maximum and what would the maximum do to it? So, production costs, much like anything else, will have a curve. And max production would be at your max or your extrema. Most companies run in this box area. So most companies run in between max production. Sometimes they go over, sometimes they go under, depending on supply and demand. That's when quality starts to go down. So things break. What happened to Apple?
Oh, yes.
True. They tried to like mass produce a bunch of iPhones and then they were all poor quality. They all started breaking. Batteries were going bad.
Same thing happened with Samsung.
That's what happened to all the notes that blew up.
That's actually incorrect because they started using other companies to produce their batteries.
What happened?
Samsung started outsourcing their
Yeah,
battery
to
production.
China.
And then one of the companies that was producing them.
Hi, George.